Hello everyone, and welcome back to our class in Artificial Intelligence and its application in finance. In this video, we are going to start the subsection on neural networks, and to be precise, artificial neural networks, because these are obviously not biological networks we are looking at, but artificial ones. And as I mentioned in one of the first videos, artificial neural networks try to mimic the behavior of the human brain and tries to mimic the processes that happen in the human brain, encompassing neurons and synapses. And consequently, the term neural network actually encompasses a large class of models. We're going to look at the single layer perceptron, or the single hidden layer backpropagation network. It's usually just referred to as the single layer perceptron. This is a very plain vanilla neural network. There are more complicated ones, more complex ones. We will also shortly cover deeper networks, so-called multi-layer perceptrons or MLPs. And after having seen regression and classification trees, you're probably understanding why and what is meant with deeper networks and deeper models. And the same happens here with neural networks. If you're more interested in neural networks and what can be done on top of neural networks, including the single layer and the multi-layer perceptrons, you can have a look at the Hastie, Tibshirani, and Friedman and the Goodfellow, Bengio, and Corville textbooks. Actually, both should be available for free as open source books on the internet, and you can learn more about artificial neural networks. Now, as I mentioned in the first video, actually, I think neural networks, artificial neural networks, are far from being new and have been around for 80, 90 years. In fact, they date back to the 1940s. They have since gone by many names. Used to be part of cybernetics, then was known as connectionism, then was just neural networks, artificial neural networks. Nowadays, it is commonly referred to as deep learning. Why has it become more important? Why have these models become more sophisticated? Well, because we have more data to train these models. We have big data available. We have more computing power, and as a result, these models have grown in size with increasing power of hardware and software. And nowadays, with the availability of big data samples and the availability of large clusters and powerful computers, these models can be put to a better use than this was possible, say, in the 80s or 90s. And since then, neural networks have helped to solve increasingly complicated applications with increasing accuracy. What is the structure of a neural network? Very simply, this is a single hidden layer feed-forward neural network. It's a single layer perceptron. Sorry, not multiple, but a single hidden layer perceptron. And what happens is, here, we start out with our features x1, x2, and so on until xp. So again, just like in the traditional linear regression setting or the classification setting, we have p features. Could be, for example, age, could be gender, could be income, could be maybe home region. And then what we do in the neural network, in the single layer feed-forward neural network, we combine these features linearly in the first and only, in this case, hidden layer. So we're constructing variables z1, z2, and so on until zm, and we are linearly combining these features to form, for example, z1. Obviously, this is basically a linear regression. We have coefficients that in this case will be called weights, and these weights need to be estimated. So what we get is, one could say, a couple of regression analysis results, a couple of variables that are hidden. Why are they called hidden? Because these are not observable. We can only observe y. Those are our responses, and we can observe our features. For example, let's say this is the insurance premium data set. So we have age, gender, income, and so on. And these are the it's the insurance premium example, we would only have one response. But actually these models are able to predict not just one response variable, but also multiple classes or multiple metric variables. So in the very simple example of the insurance premium dataset, we would only have Y1. We are going to predict insurance premium, and then this would be the insurance premium, and these would be the features. So what we are doing is we are inserting yet another layer in between, and before combining the features directly, as we would do in the regression analysis or in a regression tree, instead of directly using the features to predict Y, we first compute these hidden and unobservable variables Z1 to Zm, and then we are recombining these variables for our prediction of Y. That's the only thing that is different, basically, in comparison to a linear regression model or linear classification. Now, why are we doing this? Well, by inserting this additional hidden layer, we can make and we can do more transformations of the data, and thus we get more flexible models. That's basically it. That's also why, if you take the Hasty Tibshirani-Friedman textbook, it will tell you that, well, neural networks are far from being magic. It's simply a generalization, a nonlinear generalization of a regression model. So that's what basically at least the single layer perceptron is. So it can be seen as a two-stage regression or classification model. It can be done for both regression and classification, where we have the hidden features in this hidden intermediate layer, and they are derived as a nonlinear function of the inputs. And we'll see this in just a bit, what is done to the features x1 to xp in order to derive these hidden features z1 to zn. These features, these hidden features, are then used to model the responses, the targets y1 to yk. For regression, you will usually set k equal to 1 and employ only one output node. That's what we did here when thinking about the insurance premium dataset. For classification, obviously with k classes, we can use the k outputs. So we have y1, y2 until yk. And then they will be coded 0, 1 binary variables. We could say this is, let's say, the class of, say, low income. This is middle income, and then we have a third class that is high income customers maybe. Okay. Now to the formal description. We start out with the hidden layer. That's the hidden layer in this line. What we are doing is we are using the features. Somebody has to highlight this. We're using the features x. These are observable. We combine them linearly. So we have actually the intercept in this case is called the bias, and the regression coefficients are called weights. We have a linear combination of our features. We have a linear combination of our features, and if we were to set sigma to the identity function, then we would simply get a linear regression model. Then Z1, Z2, etc. would simply be a linear transformation of x of the features. But usually sigma, which is the so-called activation function, is often chosen to be the sigmoid function, which is given here. And this is a nonlinear function. So our linear combination of the features is nonlinearly transformed, and we get the hidden layer. And these hidden layers are then again linearly combined to yield tk, and then we can apply yet another nonlinear function, gk, to t, and this is our prediction for y. So this basically is, let me use a red line here. This is basically our prediction for yk. So it's no magic, it's very simple. Take the features, combine it linearly, apply the sigmoid function to this, you get the hidden layer, recombine those hidden features in a linear fashion, and then you can apply yet another nonlinear function, g, to those transform variables tk, and you get your prediction for y. That's the sigmoid function. One can also use the rectified linear unit function. This is given by the maximum of 0 or nu, but that's basically the single hidden layer perceptron. Now, FK is the model's prediction. We've seen that, and these predictions are constructed as a linear combination of the hidden features, and we have a final transformation GK. In regression analyses, usually one does not use this final transformation, so GK is just the identity function. So basically what you're saying is our prediction is K, and we don't apply any function GK to it. But in classification, one usually uses the softmax function, and this is actually the same as in the multi-logit model you might have seen in regression analysis. Okay, so that's the single layer perceptron. The units are called hidden units in the hidden layer. They are not directly observable. They are learned from the features x1 through xp. These hidden features are then used to produce our predictions on the output features. They are again observable. And when sigma is the identity function, the whole model collapses to a linear model in the inputs. It's no big difference to a linear classification model or a linear regression model. So one actually needs, for example, the sigmoid function to get a generalization of the linear model and to have any extension of the linear model. Otherwise, it doesn't make too much sense. And what are multi-layer perceptrons now? Well, it's very simple. If you do this again, if you insert yet another layer and say, okay, I'm combining these 3 here, and I'm combining these 4 maybe, and we get a second hidden layer, then we have a 2-layer perceptron, and this will give us a deeper model. And if we have another and another, these all are called multi-layer perceptrons. Okay, stacking multiple hidden layers on each other will give us the MLP. And if you want to see a very excellent graphical illustration of a neural network, if it's not clear by now, you can actually look at this video here on YouTube, which is a very, very good example and illustration of what a neural network does. Let me comment on one thing, and let me delete a little bit of my drawings here. Why is it called a perceptron? Why is it called an artificial neural network? Well, actually, what happens is, usually in the human brain, at least that's what we think of, neurons and synapses. The nodes are the neurons, and those edges, these are the synapses. So what happens is, we have a signal. Let's think about this maybe if this is the human eye, or human brain. We get a signal that starts out here, and we get a signal here. So for example, we have a male person, this is 1, and for this feature we have a 0, and here we have a 1, 0, 0. Now, based from our actually in the training process, we can see that, okay, if we have a 1 here, and if we have a 1 here, then this hidden neuron is activated, so it's set to 1. These are set to 0, and then we would see then suddenly, okay, we can observe 1. What happens is that in the training process, we see that if we have 1 here, if we have a 1 here, then we have 1 here, and then we set the parameters, which are the weights. Let me just check. This should be in the first, this should be alpha, and then we have beta. So this alpha, and this beta, they are increased to make sure that if we have 1 here, if we have 1 here, then we get to this one. And then these signals come in, they are transported via the synapses, and then we get to this point. if we have a 1 here, if we have a signal coming in here and here, maybe these are the weights that have been trained, have been increased, and then we get to this point. And this is how actually the artificial neural network and also the human brain works. We get signals coming into the neurons, we have synapses that have been trained, we remember certain things, and then we can decide on whether, for example, we are looking at a cat or a dog. So this is what is also illustrated in the video, and you can see this especially when looking at the sigmoid function. Again, this is the nonlinear transformation of the linear combination of the features, and what happens is, if actually this were a linear function, then we would see, okay, maybe it looks like this. We get a small value coming in, we get a small value. If it's a slightly higher value, we get a slightly higher value, etc. But what is actually done is we have a nonlinear transformation that is also governed by this parameter s. That's a scaling parameter in the sigmoid function. And if you look at the extreme example of s equal to 10, then actually what happens is you get the purple function here, meaning that for all small values below 0 coming in, you have no activation. The resulting function is 0, the function value. If it's a positive value, then actually it's a 1. So you can see for this extreme choice of the sigmoid function how this actually works. This pretty much looks like, delete all this again. This is pretty much like a signaling function that if you have enough neurons that are being switched on, or the right neurons that are being switched on, then the sigmoid function with this choice of scaling parameter will lead to, let's say, 1, 1, 0, 0, 0, 0. Then some hidden units are switched on, others are switched off. And now it becomes clear how this network works. Okay, so this is the structure of a neural network. In the next video, we are going to have a look at how to fit these neural networks, which means we have to estimate and train those parameters alpha and beta.